In this video, I will spend a few minutes going over the conceptual picture of what these two charge densities represent when we calculate the potential and the electric field from a polarized object. So what I have here is a macroscopic object that is polarized. So you can think about an insulator where I bring nearby some external charge and I end up polarizing this insulator. Now, this is the case, this is my first example where all atomic dipoles here are exactly the same. The polarization is uniform here. Every dipole moment is exactly the same, points in the same direction, and it has the same magnitude. Now, I want to remind you what the theory is, what we found for, if you want to find the potential at your observation location, then you have to add two integrals. You have to assume that you have a surface charge density on the surface, and this integral will give you the contribution to the potential from your surface charge density. And you have to also assume that you have a volume charge density, and the integral of that will give you the contribution to the potential. Now, how to find the two charge densities? The surface charge density is just the polarization dot product with the vector, the unit vector that is normal to your area, and the volume charge density is minus the divergence of polarization. Now, I want to remind you though, I want to do something to show you what this means. I'm gonna keep the minus sign, and what the divergence will give me is minus the partial derivative of px and the partial derivative of y and the partial derivative of z. Now, I want to think about a little bit what this quantity here is showing me. This is essentially how this first term represents how much polarization changes with a small change in the x direction. The second term is showing me how much the y component of polarization changes with a small change in the y direction, and the same thing for the z. So overall, this is showing me how much polarization changes. Now, in the case where all the dipole moments are the same, this would mean that polarization it's the same everywhere, and that means that there would be no change. So the volume charge density in this case would be 0 for the case where I have uniform polarization, the same atomic dipole moments everywhere. This term would go to 0. What does that mean now? If I go back to my picture, what this means is that essentially you can think about, let's do this. Essentially, this means that you can forget about everything that is going on here. It doesn't matter what dipoles you have here. Now, if I do the calculation, I have polarization, it's uniform everywhere, dot n hat. I will get a non-zero surface charge density. I do have some charges. Here it will be negative charges, here it will be positive charges on the two sides of my insulator. So I will have a sigma b here, and I will have the sigma b here. This is my surface charge density here and here. I will have those, but in the case of a uniformly polarized insulator, those surface charges really are what matters when I want to find the potential. Now, so in the case of uniform polarization, you can forget about the volume bound charges. Now, in the case where you have a non-uniform polarization, okay, either because the dipole moments have a different magnitude or because the dipole moments point in different directions, at the end of the day, in this case, polarization is non-uniform. And this means when you go to calculate the divergence of polarization, in this case you will find it to be non-zero. So the way that we will think about this problem, we will say, all right, let's divide this into segments. So here I will have some surface charges, and here I will have some surface charges, and whatever is going on inside in the interior, not on the surface, I will take it into account by using that volume charge density of the bound charges, and this will depend on the divergence of polarization in the inside. Okay, so this is using the surface charge density and the bound charge density just allows me to think. Now if I can do a little bit better 2D picture. All right, this allows me to say, okay, you can think about what the charges on the surface contribute to your observation location, and you can also think about what the volume polarization charges contribute to your observation location, and then you can just add those two contributions. Now, the important thing to keep in mind is that the surface charge density and the volume charge density of polarization, they have a different dependence on polarization. The volume one depends on the divergence, whereas this one, the surface charge density, is just the dot product between polarization and the unit normal vector.